Hey there, Kevin Squad. In today's lesson, you're going to need your periodic table. Um, you're also going to need another periodic table handout that looks like this. Now, I do have copies of this in our classroom, so if you don't actually have a printer to print this one off, you can actually get it from me the next time you see me. Otherwise, there should be a link available for you to print off this periodic table because we'll be filling it in. All right, so like I said, you need your periodic table today. The topic of discussion is actually on something called electron configurations. Now, this is something that if you were looking at your notes package, I do have a section on electron configurations. It's not a bad resource for you to look over, especially if you're not really understanding what I'm saying here. But I think that you'll understand this particular lesson better than reading through the notes. So let's kind of just get started and see how things go. Now, we've already gone through things like the quantum model. Okay, so if I were to start with a quantum model of, let's say, this particular substance. See if you guys can figure out which one this is. If that is my quantum model of an atom, hopefully at this point you guys will recognize that this is helium. Okay. You should know it's helium because it only has 2 electrons, and those 2 electrons are in a 1s orbital. Okay, so an s orbital, so a sphere-shaped orbital. Now, this one by itself isn't necessarily hard to draw out, but if I gave you something that is more complex, like sodium or magnesium, there'll be a lot more for you to draw out. Now, there is a way that we can represent atoms, have all this information that the quantum model would have, without actually drawing out the quantum model itself. That is what we call electron configuration. So this is our quantum model. Any quantum model can be set up as a electron configuration. So the electron configuration I'm just going to abbreviate this from now on with EC. Okay. It gives you the most important information about the quantum model, about that particular atom. So for helium, I would write the electron configuration like this. This would be the electron configuration for helium. So let's examine all the different parts of this. What do we actually have? Well, the number 1. Okay, that number, the first large number, the coefficient in front of the letter, is always the quantum number. And you guys know that the quantum number is basically the main energy level, or principal energy level. That this particular atom would have. Now, at this main energy level, you have the letter. This is the type of orbital. So again, nothing new. You already know that we have letters S, P, D, and F to represent orbital types. Now on to the exponent number. Okay. The exponent number always represents the number of electrons in that orbital. So number of electrons currently in the orbital. So what we're looking at is, we're looking at an s orbital at the first energy level with 2 electrons. So here you have the s orbital, okay, the first s orbital with quantum number 1 with 2 electrons. So this is the electron configuration for helium. All atoms on the periodic table have their own electron configuration. Okay, I started here with 1s2 for helium, but if I wanted, just as a side note, what is hydrogen's? Right? What would its electron configuration be? Well, it is the most simplest one, right? It's also 1s, but because the s orbital only has 1 electron, it's 1s1, whereas helium is 1s2. So if we had 1s3, oops, sorry, my fault, my mistake. That is like a rookie mistake. There's no such thing as a 1s3. Okay, actually, maybe I should actually go through that. If you see someone write something like this, this is wrong. Okay, there's no such thing because s orbitals can only hold a maximum of 2, not 3. So the maximum of 2 electrons is reached. So what happens now? I have an extra electron that I need to put somewhere for the next element, which is lithium. So what I can do, if this 1s2 represents helium, okay, what is the next set of orbitals? Well, that should be a 2s. And the 2s would only have that 1 electron. So in total, I have 3 electrons for the substance. So 3 electrons in total. Okay, that tells me that this is lithium, Li. Okay, the electron configuration tells me what orbital types make up lithium, so that if I have to draw it out now, I know that lithium would have a 1s orbital as well as a 2s orbital. Alright, so here's my 2s, here's my 1s. My 1s has 2 electrons, right? So it's 1s2, and my 2s has 1 electron, which is 2s1. So that the nucleus is kind of bothering me here, so I'm just going to make it way more like a nucleus, so you don't confuse it as an electron. Okay. So because your electron configuration tells you all the orbital types and what energy levels they're at, as well as the number of electrons, this is a much more convenient way of showing information than by drawing a quantum model. Okay, so there are some tips and hints and some exceptions that we come across when we go through different atoms, and that's why your periodic table is a good thing to have. I mentioned before that this is like your Bible for chemistry, because all the information that you need for quantum chem is basically arranged on the periodic table. So if you know how to read it, you would know how to use it. Okay? And you don't ever have to memorize things. So I'm just going to zoom out a bit so you can see the whole table. I think I've already gotten you to label the quantum numbers, okay, on the side here. But if you don't remember doing that, or you don't have it, just make sure that you have the quantum numbers here, like this. Okay. These quantum numbers are actually for the s orbitals. Okay. Now, I don't want you to mark up your periodic table. Okay. That's what the blank periodic table is for. What I want to just kind of show you here is how the periodic table is arranged. So this whole section here, I'm going to highlight this yellow here. Again, don't do this on your periodic table. Just kind of watch and listen. Okay. So I have a block of, I've blocked off this section of the periodic table. Now, the other thing that I should also block off is this space here. Okay. Because technically, helium exists there, right next to hydrogen, in the S block. So this whole yellow section represents your s orbitals. You have your 1s orbital, 2s orbital, 3s orbital, 4s orbital, 5s orbital, 6s orbital, 7s orbital. Okay. That part I think most of you guys understand. This part here make up your p orbitals. Okay. It's what we call the p block. So these are the p orbitals. Now, in the previous lesson, I explained why there is no such thing as a 1p. So your p orbitals, what happens here is they start with 2p. Okay. So your s orbitals always start with 1s, and you have 2s, 3s, 4s, 5s. Here, you start with 2p, and this would be 3p, 4p, 5p, 6p, 7p, if you go down that far. Okay? Now, let's look at the middle block. The middle block, these guys represent your d orbitals. They happen to be all your transition metals too. Now, similar to your p orbitals, there's no such thing as a 1d. There's actually no such thing as a 2d either. The d's actually start with a 3. So you have 3d, 4d, 5d, 6d. Okay. Now, what you have to be careful of is when you look on the left hand side, okay, when you look at the 4s, okay, the fourth quantum number, the fourth row, the d block, the 3d's actually are in the same row as the 4s. Okay. On the left hand side you have 4s, on the right hand side you have 4p, but in the middle you don't have 4d. You start with 3d. Okay? This is an inconsistency only because these d orbitals are very large and they happen to be overlapping the third energy level and the fourth energy level. Okay? So 3d, like this middle block here, should technically be shifted slightly upwards, okay, into the third energy level. Okay, but because they wanted to not have the periodic table look weird, okay, they just shifted it downwards so that it actually fits with the fourth energy level. But they technically start at the third. Okay, so that means you have 3D, 4D, 5D, and 6D. Moving down, there's only one more block left, and that is your F block. So these two rows, they actually exist here. Okay, they just got pulled out. Okay, so your F block exists between, so these are the F orbitals. So your F block, they exist between the S and the D's at atomic number 57 to 70, and again at 89 to 102. For this particular group of orbitals, they start with 4F, and there's only two rows, so you only have a 4F and a 5F. Okay. It's actually pretty easy to remember them. So all you have to do is remember that the S's start with 1S, the P's start with 2P, the D's start with 3D, and then the F's start with 4F. So it's 1, 2, 3, 4. Okay, and then you just count accordingly down each row. So this highlighted area, okay, if you actually do have that blank periodic table, what I want you to do is to highlight the blank areas so that you know where exactly the S block is, P block, D block, and F block. Okay, so oops, don't know what happened there. I guess I can get out. There we go. All right, so I want to draw on this. I don't know if I can now. Okay, I think I should. So this is your S. This is my S block. So again, you can either color or highlight. Okay, as long as you know the S block is on the left-hand side here, and it starts with 1S. Your P block is this block here. Okay, so this is your P block for your P orbitals, and it starts with 2P down there, and it goes down 3P, 4P, 5P, 6P. Okay, so if you want, it's 3P, 4P, 5P, 6P, 7P, and this is your 2S, 3S, 4S, 5S, 6S, 7S. Okay, and that makes the middle part your D block, and D block starts with 3D, and you have 4D, 5D, 6D over here, and then finally your F block, or the lanthanide and actinide series, and they start with 4F, and you have 5F down here. Okay, so this is meant as kind of a visual guide, so that if you ever get lost in terms of which orbital you're at, you can kind of check. But I'm going to teach you how to use your periodic table because honestly, you don't necessarily need to know or memorize everything here. Okay, if you can basically just count the atomic numbers and know when it changes from S to D to P to F, that's really all you really need. So let's do this by giving you another example, and then we'll work more in class on some of the harder ones. I want you, let's see, example, let's give you two. I want you to write the electron configuration for, let's go with chlorine, and after that I want you to try and write the electron configuration for something like iron. Okay, so for each one you always have to start with 1s. Okay, 1s is your basic atom for hydrogen, so you start with 1s and you work your way up to chlorine and iron. So a good thing to do is look at where chlorine is. Chlorine is over here. So that means the last set of orbitals that you have to write in are the p orbitals, specifically the 3 p's. For iron, the last set of orbitals that you're going to write in are the 3d orbitals. Okay, so if we start with hydrogen and we work all the way up to chlorine, what's the electron configuration? Same thing for iron. What would be the electron configuration? So you can pause the video now, try and figure that particular one out, and then when you're done, just resume the video. Alright, so I trust that you've gone through both sample questions. Let's look at how you did. Okay, so we know we have to start with 1s. If we start with 1s, okay, it'll be 1s1, 1s2. So once the orbitals are filled, we move to the next orbital. Okay, so for chlorine, once 1s2 is filled, you drop down to 2s. Okay, so 2s is right here. We know that we're going to fill in both orbitals or both components of that orbital. So 2s2 is basically all filled up, right? So after 2s, well, where do you move to? Okay. You're going from atomic number 4 all the way to atomic number 5. Okay. So from 2s2, you go to 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. 2p6 is basically neon. So 2p6. After neon, you drop down another energy level to the 3s. Okay. So 3s1 is going to be filled, 3s2 is going to be filled. Then we move over here where you have the 3p's. So once you get to the 3p, chlorine is in a 3p. So you just have to count where it's positioned at. So it's going to be 1, 2, 3, 4, 5. Chlorine occupies 3p5. Okay, so this is the valence, or technically they're the valence electrons of chlorine. Okay, they're in the outermost orbital. In a Bohr model, the valence electron for chlorine is 7, and that's because they're looking at shells, right? So you have to incorporate the 2 electrons from the 3s. But in a quantum mechanic model, the valence electrons are in, more specifically, the 3p's. So in this case, 3p5. So if you were to add all of those superscript numbers, okay, all the numbers that represents the electrons, it should add up to 17, okay, because chlorine should have a total of 17 electrons. Okay, so if you add 1, 2, 4, plus 6, plus 2, plus 5, that should equal to 17. Okay. So let's look at iron. Iron does pretty much the same thing. It's just that it's lower on the periodic table. Okay, so once we finish the 3 P's, we drop down to the 4 S's. Okay, and once we finish the 4S, it starts with the 3 D's. So the easiest thing that we can do for iron, we know that's going to be 1s2, 2s2, 2p6, 3s2. In the p orbitals, we filled it all the way full, so it's 3p6. We drop down to the next s orbital, which is 4s. It gets filled in with 2 electrons, so it's 4s2. And then we enter the 3ds. Okay, so we're at the 3ds. Now, this is electron configuration in the order of electron filling. Okay, some textbooks will switch placements between 3D and 4S so that they're numerically increasing. I rather you leave it like this, okay, because it's easier for you to just carry on without moving things around. Okay, it's actually a little bit more accurate because this is exactly how electrons fill. They will fill in the 4s orbital first before they fill in the 3ds. So when we look at how many electrons to give the 3ds, again, all we have to do is count where iron is. So iron is at 3d1, 3d2, 3d3, 3d4, 3d5, 3d6. Okay, so 3d6 represents the valence electrons of iron. Okay, and again, if you add up all the electrons that we have here, it should equal the atomic number of iron as well. So this part with the 3 S's, 3p, and then 3d, okay, with the 4s in between, this is just electron configurations with the proper electron filling. Let's see if I can write that in. Proper electron configuration based on electron filling. So 4s is filled before 3ds. And again, that's just based on your periodic table as well. Okay. Hopefully this makes some sense. Like I said, if you need more sample questions or a different way of explaining it, look at the notes package I gave you under the electron configuration section. Okay, it should give you a little bit more. Just don't read too far ahead, because there are some exceptions that I would like to go through with you so that you guys can understand those as well. And I don't want you to be confused beforehand. Okay, well, that's all I have for today. Hope to see you guys soon. Thank you.